My name is Renellys Perez. I'm in the Physical Oceanography Division here, and I'm going to be telling you about the Tropical Atlantic Current Observation Study, or TACOS, and today is TACOS Tuesday, so it's appropriate that I give you an update because I give weekly updates to the group on Tuesdays, so you can all consider yourself honorary members of the group today. And what TACOS is a bunch of instruments that are measuring currents, so measuring upper ocean velocities. And we augmented the 4 north, and I'll try to use the pointer so that those listening in remotely can see what I'm pointing at, the 4 north 23 west P&E mooring. So that is the Parada Northeast Extension, which is part of the U.S. contribution to the Parada Array. So all of those symbols are showing you moored buoys that are part of the Parada Array, which is a collaboration between the U.S., France, and Brazil. And because these instruments are out there and they're making measurements of temperature, salinity, and meteorological measurements, and they're also making one measurement of velocity, they're just out there and we can augment them and make ancillary measurements and do pilot and process studies. Okay, the U.S. contribution to Parada is funded through NOAA's OOMD, Ocean Observation and Monitoring Division, which will soon be a new acronym called GOMO, which is Global Ocean Modeling. I'll have to learn a new acronym. But for as of today, it's OOMD. Okay, so I'm going to tell you primarily about the first year of data we've collected from these moorings. I'll show you some early data coming in from the second year of data, some early images of the second year of data. And what these instruments are telling us about is the upper ocean horizontal velocity and vertical shear with pretty fine vertical resolution, 5 to 20 meter spacing. So that's how I define pretty fine. Okay, so why do we need moored velocity measurements in this location and in the upper 100 meters? Well, we have a bunch of other platforms that are sampling velocity in this region. We have drifters, which we can deploy in the equatorial region, but they typically don't tend to cross the cold tongue front, and they quickly, because of the surface circulation, quickly diverge away from the equator when we put them in there. And this is just showing you a sample trajectory of a drifter that was deployed north. This black line is showing you the cold tongue front as it's in space and time as the drifter's moving along, and the drifter is staying to the north of the front, so it's not crossing the front. So, drifters don't stay at the equator and they don't like to cross the cold tongue front. ADCP sections, we go out there on annual cruises and we get shipboard ADCP and lowered ADCP sections. So during the cruise, while you're out there, you get this really high spatial resolution information, you get vertical profiles, but you're only out there once a year and you've got to average a lot of these repeated sections together to get a mean picture of what's happening. And you have very little information in the upper 30 meters because you're measuring from the ship and there's this sort of blind spot where you don't get usable data. We use satellite data to estimate geostrophic velocities and wind-driven Ekman velocities, but because this is so close to the equator, your Coriolis term vanishes and you have lots of problems using these products to infer the flow near the equator. So you can come up with techniques to get around that, but it's not optimal. Okay, so we need moored current measurements in the tropical Atlantic in the upper 100 meters. Okay, so we need moored measurements, but why do we actually need the data itself? Why do we care about velocity? Well, in this region, we care a lot about the ocean-atmospheric interactions. For example, Atlantic hurricanes depend on the sea surface temperatures in the region, and changes in the sea surface temperature patterns in this region can affect the rainfall over neighboring continents. So we care about ocean-atmosphere interactions. And it turns out that the vertical variations in velocity are really important for setting temperature, salinity, ocean fluxes, mixing and turbulence, and those air-sea fluxes in the region. And so we don't just want to know what the mean state is, we want to know how the currents are changing in response to very short timescale wind events and eddies and waves that are in the region. The last reason is that models, it might shock you to find this out, have biases in temperature. And so it's good to have these observations that can provide a really rigorous test to compare with the models and to try to understand whether models are getting these wind forcing events and eddies and waves, if they're getting those interactions with the mean circulation correct. On the left, I'm showing an image of the instruments as they were getting ready to be deployed on the first cruise, so the first year of data, during the 2017 P&E cruise. And these instruments were funded by the division, by the Physical Oceanography Division. And so we put them out in the water and collected the first year of data. This is where we put those instruments. As I said, we have between 5 and 20 meter resolution. So you see at the top, they're really tightly packed. You have 5 to 10 meter spacing. Then towards the bottom, you have 20 meter spacing. And again, on the right is the next generation Atlas mooring, or the T-Flex mooring. And this is the instrument that's there already. Yes, Molly?
Just to go back to the last so if the main goal is to understand hurricanes, is that right? Or
no, it's the
more north. If it seems that that's south of
the main goal is to understand upper ocean velocity variability, but the reason why that is important is because it affects the ITCZ, it affects all kinds of things which affect ocean-atmosphere interactions, and one of them is hurricanes.
So you have moorings that are all up along that 20 west. Why?
Right.
Why 4 north versus one of the other?
So we picked 4 north because that's the area where you have the tropical instability waves playing a big role. That's the furthest south of the Parada Northeast Extension moorings. And this was sort of a test bed. We're doing it here, and then the idea is down the line, we can use the information that we glean here about the upper 100-meter structure to then put a reduced configuration at all 4 of the moorings. So that's where we're moving towards. So yeah, good question. Okay. All right. So this is where the sensors are. The red on the left is showing you where all of the Parada Northeast Extension moorings are sampling velocity now at 12 meters depth. So on the new T-Flex configuration, they're all making a standard velocity measurement at that depth. Historically, that measurement was made at 10 meters depth with the older iteration of the Atlas moorings. So we have a 12-year record, it's a bit gappy, of velocities at 10 meters depth to compare against. Okay, so that's, and then on the right is showing you all of the temperature and conductivity, which is a proxy for salinity, measurements that are being made as a standard suite of measurements that are being made by the mooring. Okay, so 2018 came along, and we didn't have enough spares to do an at-sea turnaround for the instruments. And so we contacted PMEL, and they kindly loaned us 4 of their instruments from their pool so that we could do a reduced deployment and not lose this valuable, the opportunity to continue to collect data. This data is now being served from this year on their website, so PMEL's Parada website. And I didn't mention it earlier, but the data is coming in real time. Once a day, we get hourly data from the mooring. So it's quite nice. You can watch the data just coming in, and which is fantastic when the data makes sense. And when it doesn't make sense is just puzzling because you don't know enough to understand what it's observing. So you have to just wait for more data. Okay, so we didn't have enough to instrument all the depths, so we put out 4 sensors, and we didn't pick those depths at random. We had the first year of data, so we did vertical decorrelation scale calculations, and we realized, okay, so the instrument's making a 12-meter measurement, but we wanted some redundancy in the surface mix layer, so we put in an instrument at 27 meters. And then we looked for depths where the flow was really not correlated with the surface or was capturing a flow feature that we wanted to capture, and we distributed them based on that information. We did a pretty good job with the velocities, but the spoiler is that we missed some of the shears with this deployment. So the spacing was good for velocity, not so good for some of the fine scale shears that we observed in Takehome 1. Okay, so I'm already running behind. Okay, so Takehome was situated, just for your orientation, between the westward flowing south equatorial current and the eastward flowing north equatorial countercurrent. They're situated to the north of the mean position of the cold tongue front. So this is the cold tongue here in blue. So you see it in temperature. And the mean position of the cold tongue front is like 2 north. And here's the mooring. Okay, but when you have these tropical instability waves coming by, and you can see that how they perturb sea surface temperatures, for example, during a given snapshot, the front can move past the mooring. And so you can see a cold anomaly as the front is moving past the mooring. And associated with that is a velocity signal. So you can have velocity perturbations on the order of a meter per second. The periods of these waves are 14 to 50 days, and the zonal wavelengths are about 1,000 kilometers, and they're moving past westward with a speed of 20 to 50 centimeters per second. Okay, so that's the mean flow that we'd expect to see. The NECC's got a mean of about 20 centimeters per second. The SEC can have a much stronger mean, like 30, 40 centimeters per second. Okay, the expected meridional currents are much weaker. The scale has shifted from minus 50 to 50 to minus 25 to 25. The mooring should see part of the tropical cells. In the Atlantic, you have a tropical cell on either side of the equator. And so you should see wind-driven poleward flow at the surface, and you should see a return geostrophic flow underneath. So you should see northward flow at the surface and southward flow underneath. But the mean will be really small, between 5 and 10 centimeters per second, and much smaller than those 100 centimeter per second perturbations that we might see during a tropical instability wave. Okay, so that's enough orientation and background information. Now I'll tell you about the observations in the first year of TACOS. We were deployed from March 6th, 2017 to March 26th. So if I show you a record mean, it's a little bit over a year, and it's March to March, not a calendar year. And this is part of a paper that we're working on. We're revising it to submit to JGR. And what this paper focuses on, and what I'm mostly focusing on during my presentation, is the daily to intraseasonal variability. So kind of like daily to 2 days to like 90-day variability, going throughout the whole record that we observed. There are really fascinating diurnal variations, and I'm not going to tell you too much about it. It's part of a study that Greg's leading and part of a study that Jonathan and I are working on. And so stay tuned for their seminars when they tell you about all of this data. But for this study, we're focusing on the 2-day to sort of the whole record length phenomenon that we observed. Okay. Last thing I want to tell you, the data is hourly. We have 384 days of it. 8 sensors collected data for those whole 384 days. The 37 meter failed throughout, about halfway through the record. And so we vertically interpolated across the 2 adjacent moorings. So we took the 32 and 47 to interpolate across. 87 meters, we only got 3 months of data, so I don't really look at that in much of the analysis because it just died so quickly. And then the near surface mooring at 7 meters died after 9 months, so we only got through the end of 2017 with that data. Okay, so this is what it looks like. These are the near surface fields from TACOS. Black is the 7 meter velocities, so you have the zonal component and the meridional component, and red is the 12 meter velocities. So you can see that when we had both of them, they were pretty much one on top of the other. They were very strongly correlated with one another. So you can, after that 7 meter sensor failed, you can use the 12 meter as sort of a proxy for what's happening at 7 meters. Okay, an imperfect, it's better to have 7 meters, but that's what we have. The other thing that is on this graph is a sort of a seasonal cycle. I took all of the data that was at 10 meters depth for the 12 years that we had that sensor at 10 meters depth, and I put them all together and I averaged them by calendar day. So I took all the January 1st and averaged them, and then I also computed the standard deviation. So that's what the line is that you see here, the gray line is. And that's what the envelope, that gray shading is, the standard deviation. And then I applied a 30-day low-pass filter. I just wanted to see what the sort of the seasonal evolution was in the historical record. There's not much of a seasonal cycle here at 4 North, 23 West, and that's kind of what I just wanted to show you, that there's not much of a seasonal cycle. But you can see when there's time periods like here, the shading envelope is pretty spread out, so that's when you tend to see tropical instability waves. So you have a lot of variability during this time. And so the other reason why I wanted to show you this is that zonal velocity doesn't really lie outside of the bounds of what was expected for much of the TACOS record. This is showing you the time series as a function of calendar day, which I like, but for reference, the months and the years are identified on the graph. In contrast, zonal velocity is pretty much contained within the bounds that we expect. In contrast, the meridional velocity signal a lot of times is out of those bounds. This is particularly true from May to August, where you have these three really strong tropical instability waves. And I've filtered these all with the 48-day low-pass filter. If I hadn't, the amplitudes of them would reach 80 to 100 centimeters per second. So some of that variability is very high frequency variability associated with the record. There are also a series of 3 TIWs that come up later in the year, and this is not the best graph to show it, so you'll see it when I show the next images coming up. The other thing that I want to call your attention to is there's a series of super inertial oscillations. There are oscillations with a 4 to 7 day period that happened in the fall. Okay. All right, but taking a step back from all of that high frequency variability, I want to show you the record means at all of the sensors as a function of depth. And I want to compare those with the historical values that I have. So the black line is an average of all of the shipboard ADCP data that was made by a study that we did in 2014. So it's all of the shipboard data collected along 23 West. And then we extrapolate upwards to the drifter means at the surface. And so what you can see is the TACOs means, which are given to you in red, and the error bars are the standard errors, pretty much lie on top of those lines within the uncertainty. So it was actually quite surprising to see that was the case, because we just had 36 cruises that we averaged together and to generate our mean. Okay, and there was no guarantee that the record mean would look like the long-term mean. What the gray dot there is showing you is the 10-meter velocities from the long-term record, from the 12-year record at the 10-meter depth. So meridional velocity agrees quite well, but the zonal velocity does not. So the zonal velocities we expected to see based on the long-term record was 10 centimeters per second, and we actually saw velocities about 2 to 3 centimeters per second, so much weaker. General properties that you observe, the flow is pretty much northward at the surface, becomes northeastward as you're moving down the water column. It has its maximum eastward flow, about 32, 37 meters depth in this range. And then it becomes southeastward as you're going down the water column. And the values are all really weak, like I said. The values are all between 5 and 10 centimeters per second. And this is because the flow is so oscillatory. So if I computed the mean of the magnitude of the velocity, I would get values of about 20 centimeters per second all the way down the water column, because you have very strongly oscillatory flow. Okay. So the question is this just because we're averaging over different time periods? Is this because we're averaging from March to March? Is there really interannual variability? Have we aliased some kind of variability in there by going from March to March? What's going on? Is the south equatorial current, north equatorial current, the boundary between the two, is it shifted closer to the mooring or further away from the mooring? What's going on here? Okay, so we can take that historical record that I showed you here to make the seasonal cycle, and I can do annual averages of the flow and construct a time series of the surface flow, just averaging all of the annual values. And this is for U and this is for V here. And so you see that black dots are showing you where the data is less gappy. So anything with a black dot, there was less than a 4-month gap in the data, which is a huge gap to have in the data. So that's just to tell you that this mooring record, even though it's really useful to look at, has a lot of gaps in it. And all of this all of this variability that we see in the middle of the record, we had really big gaps in the data during those years. And I tried to reduce those gaps by removing the seasonal cycle, but there isn't really a strong seasonal cycle. So you can't really fix the fact that you have this gappy data. You just have to live with it. And as a sign of the fact that you have high, monthly variability built in there, the old sensor at 10 meters sampled in January and March. And this dashed line is showing you what the 2-month mean was doing before TACO started. Okay, and so I said tacos had really weak eastward velocities, but the first 2 months were pretty strong. And so if I make a calendar year mean for 2017, I take 2 months of the old record, put together what I collected from tacos, I get this value here, which is about 9 centimeters per second. It's about the long-term mean. So all of this is to tell you that gaps can kill your ability to look at year-to-year variations, and that there's really high month-to-month variability that can be aliased into your annual means if you're using gappy data. So that's the take-home message. Okay, but the tacos means, I guess, what we observed here wasn't really that anomalous. It's just that we didn't observe January and February. Okay. All right, so from a model, you can see whether there's interannual variability in the model. So these are means as a function of depth, which I can't do in the observations. I don't have this vertical structure for 12 years in the data, but I can look at this in the model. And so these are showing you OFS annual means, and the thick line is the long-term mean. So you can see that there's a lot of variability from year to year. You can have a mean of 15 centimeters per second at the surface. You can have a mean of 2 centimeters per second at the surface in the zonal velocity. There's a lot of range there. And these are, okay, so this is a forced model available as 3-day snapshots, 1/10 of a degree resolution. Okay, and if I look at the evolution at the surface, I can explain some of that variability. Okay, so the black line here is showing you the evolution of the annual means at the surface. And what you see is there is year-to-year variability. You see these sort of dips and crests from year to year, but there's also this really fascinating multi-decadal variability. And I can, because I have a model and I have global fields, I can look and see what's happening in the model, and I can map out the time series of what the NECC is doing. So this is the strength of the north equatorial countercurrent, which is eastward flow, and it sits to the north of the mooring. And if I map out the peak velocity of the NECC, where the core is, it has sort of the same evolution on multi-decadal timescales. And it's got a correlation on interannual timescales of about 0.5, 0.6 with what the mooring in the model is observing. I can also look at the latitude where that peak is in the model, and it's anti-correlated with the flow that I see at 4 north. And I can also do the same thing with looking, this black line here is the boundary between the south equatorial current and the north equatorial countercurrent. So that's the line of where there's 0 zonal flow. And so what that means is if this line moves north of the mooring, so this dashed line is showing the latitude of 4 north where the mooring is. If it's north of the mooring, you should have eastward flow at the mooring. If it's south of the mooring, you should have northward flow. If it's north of the mooring, you should have eastward flow. If it's south of the mooring, you should have westward flow. Sorry about that. Okay, so that was what I found in OFS was the most strongly correlated with the strength of the flow at 4 north, 23 west. It was where is the boundary between those two big currents. So you needed to step back and look at what was happening between those two very large-scale currents to understand what's happening at 4 north. Okay, and those were anti-correlated. So if the boundary between the flow is south of the mooring, but it's kind of close to the mooring, you'd have weak eastward flow. If it's really far south of the mooring, as it is in between 2010 and 2015, you see evidence of stronger flow. Okay. So we can do this in another simulation. This is a simulation run. So this is GODAS's NCEP's GODAS Global Ocean Data Analysis System, and it assimilates temperature profiles from Parada, but it uses synthetic salinity relationships to make corrections. It's not assimilating salinity or velocity. These are available as 5-day averages. The reason why I'm showing you this product is it spans the first year of the tacos measurement. So I can look at the calendar year 2017 mean, which is this blue line here. Okay, and so GODAS thinks that there can be large year-to-year variability in the zonal means, and it thinks that 2017 was stronger than its long-term mean. So that's maybe different from what the observations are doing, but I'm trying to understand whether this interannual variability is possible, and then try to understand why it can happen within the context of these models. Okay, so what's happening in GODAS at the surface. So again, the black line is the variability in the zonal flow at 4 north, 23 west. And you see there's year-to-year variability. And in GODAS, the NECC core is actually much closer to the mooring. So the NECC core is much closer to 4 north. And so the thing that in the GODAS simulation that's most strongly correlated with the flow at 4 north is the strength of the NECC. So the strongest correlation, which is about 0.7 correlation, was between what the NECC is doing and that's what's the flow that we see at 4 north 23 west is looking like. So that's what's happening in the model framework. And what we would like to do what we would like to do is understand what's happening in the background circulation in the observational framework. So we're trying to stitch together sort of this similar picture using the drifter altimetry synthesis that Rick has put together, and using satellite data, and using the eParada data set that Greg has put together, which doesn't suffer from those temporal gaps like the Parada data does. So that's work that's still ongoing, but I think what I want you to take away from this is that it really matters what the background flow is. We've got this really rich measurements at one mooring, which is fantastic, but you want to know what the big picture is of what's happening in the vicinity of the mooring to really understand what it's observing. Okay, so let's go back to this one mooring and the rich structure that it does capture. What I want to show you here is the vertical structure of what we observed. This is zonal velocity, meridional velocity, and the two contributions to the shear from each of those components. And what you see is these 3 TIWs that I mentioned, the 3 tropical instability waves, and you can see that their presence is felt all the way. When we had that 87-meter sensor functioning, you can see that they penetrate all the way down to 87 meters. But systematically, you feel the presence of the tropical instability waves down to 67 meters. And you have very large amplitudes that make their way all the way down. And this is the first time we have this kind of observations at 4 north. We've seen these type of things at the equator, but this is the first time we see the off-equatorial structure at such fine vertical resolution. The other thing that you see is that there's strong variability in the shears, and they're on small vertical and temporal timescales. And the TIWs coming through the black line is the depth of the maximum shear squared. So you can see when the TIWs are coming through, you do have sort of interaction and modification of where you find the maximum shear. Okay, so these first 2 TIWs were really regular. They were 29.4-day periods. These last 3 that happened really late in the year, they sort of reemerged. The cold tongue sort of reemerged and these TIWs got kicked up. They had more variable periodicities between 22 and 25 days. And the superinertial oscillations that I mentioned to you earlier, you can see that their presence is felt all the way down to about 57 meters. And the depth of the maximum shear when those superinertial oscillations are going on goes down to about 50 meters. So those superinertial oscillations can affect the shear also. Okay, so how do I know that they were TIWs? How do you know that they're TIWs, even though I told you that what their periods are, and that that they have this structure that I think is TIW-like? We can look at satellite data. So we can look at satellite SST along 23 west. So this is showing you as a function of time on the x-axis and y latitude. This is the latitude of the Takehome instruments, and this is the time period on the previous figure that corresponds to maximum northward flow at the surface. And that's how I'm sort of identifying the TIWs. So you can see that when you have maximum northward flow coming across the moorings, you're bringing cold water northward from the cold tongue region. And you do see that the cold tongue starts in late spring, early summer. It weakens and then reemerges later in the fall. And that's when you have those last 3 TIWs. And you can see that the first 3 TIWs do bring this sort of like a cooling at the surface past the mooring. You can look at this another way. You can now look at this as a function of longitude and time, and you can see that you have these cooling anomalies. So in this case, I've bandpass filtered to isolate the TIWs, and you can see these cooling signatures that are propagating westward across the mooring. And so this is all from satellite data. Okay, what was unusual about this year, and I should have mentioned it, is that we were surprised to even have really strong TIWs in this year, because as the data was coming in real time, I could tell that these events were happening. But the sea surface temperatures in the cold tongue region were kind of warm. And this is kind of, this index here, the ATL3 index, is telling you about the sea surface temperatures in this box. And you can think of it as a Nino 3.4 index for the Atlantic Ocean. So when it's warm, you have sort of warm Nino-like conditions and weak TIWs. When it's cold, you have Nina-like conditions and strong TIWs. So when this data was coming in, we could see that in 2017, the ATL3 index was pretty warm. It was 0.3 degrees Celsius. And so that wasn't really consistent with seeing those strong TIWs. Okay, so that fortunately is not the only criteria for having strong TIWs. You also need to have strong shear between the south equatorial current and the north equatorial countercurrent. And it turns out, I won't, I guess I think I should pick up the pace a little bit. It turns out this is the climatological seasonal cycle of the shear between those two currents. And you can see that when it's strongly positive, that's the period of time when you have TIWs. So whenever this is, it just needs to be positive to have TIWs, but when it's strongly positive in the summer and reemerging in the late fall, that's when you typically have strong TIWs. And in 2017, the blue curve, you see that the values were about as strong as the long-term average, but you had much larger than usual values at the beginning of the season. And so the TIWs, we noticed that they were coming in a little bit earlier than usual. And you had much stronger values later in the fall, and that's consistent with having those TIWs that kicked up at the end of the year. So we're continuing to look at this data, but this is sort of like the first glimpse as to what was happening with the background shears and why the TIWs were pretty strong in 2017. They were about 50 to 75% of the most strong season that we had observed in 2009, to give you kind of a reference. So they were healthy. Okay, so we had strong TIWs. They have really amazing vertical structure. What does that matter? Why is it important? We wanted to see whether the tropical instability waves could be affecting the maximum shear depth, and that should be MSSD, not MLD at the top, I apologize, or whether it could be affecting the thermocline and temperatures. And so just what was its impact on the velocity and the vertical shear? And so this black line I showed you before, and now it's superimposed on temperature, and that's the depth where we found maximum shear as a function of time. And then the top black line is showing you what that shear was at that depth. So you can see that there is really variable shear throughout the record, and we had the strongest shear in boreal spring at the beginning of the record and in boreal winter at the end of the record. And the red line is showing the contribution from the meridional velocity, and the blue line is showing the contribution from the zonal velocity. And so unlike what we had observed before at the equator, where the equatorial undercurrent is really contributing strongly to the shear. So you would expect to see only the zonal component really contributing strongly to the shear. Here at 4 North, they're both affecting the shear. Okay, so I expected before doing this calculation that you would see the strongest shear during the TIWs. And you do see modest shear between the first 3 TIWs, and you do see modest shear during the last 3 TIWs. And you also see some elevated levels of shear after these superinertial oscillations. But again, the largest shear was when the depth of the maximum shear was the shallowest and when the thermocline was the shallowest. So it was here during this is the thermocline here in blue. It was when both of those layers were relatively shallow that you had the strongest shear observed in the record. But the tropical instability waves, even though they didn't have a super strong shear signature compared to those other 2 times of year, you do see that they did perturb the thermocline by 10 to 20 meters as they were going by. So the thermocline is seasonally evolving from a shallow state to a deeper state and then returning. But when the TIWs were coming by, you see that when the northward surface flow was coming by, you see a deepening of the thermocline. and then after the southward flow phase comes on, you see a shoaling of the thermocline. So the TIWs can exert a big change on temperatures, but at subsurface where the thermocline is. The thermocline here is, between 60 and 110 meters. So the TIWs are exerting a change on the temperatures much deeper than I sort of expected they would. Okay. What I'm showing here is, so this is the TACOS 1 data. If we had deployed the TACOS 2 configuration in 2017, this is what we would have seen. Not much. So the only thing that I really want to convey in this is that we got really lucky in the first year. We had this high resolution of data, and we observed this really fine vertical scale shear. And if we had put what we have in the water now, which is better than not putting anything in the water, we would have missed a lot of that. So this is just the exact same calculation where I just suppressed the data from where we don't have instruments right now. Okay, so resolution seems to be really important for catching these shears. Okay, we made composites for the first 3 tropical instability waves to see if they had sort of a common evolution, because they were so regular. The first 2 were 29.4 days, and then the last one we couldn't really decide when it terminated. But as you see here, I aligned them by their maximum northward flow at the surface, and you just can see by eye that the 3 curves are overlapping with each other, and the black line is the average of the 3 curves. So maybe the termination of the event, there's some more variability, but the beginning of the event is very, very striking how similar it is for all 3 TIWs. And then we can do the same thing for the vertical structure. And what I just want to draw your attention to is, if this was like a sine wave going by in this composite, you should expect to see kind of more symmetry in the pattern. And you don't really see that. You see at the beginning, you see about 2 days of surface northward flow, and below you see southward flow. This southward flow sort of makes its way up to the surface over the next 4 to 10 days. And then you see northward flow, and then again, this northward flow at the subsurface makes its way up to the surface to begin the next wave. So this is telling me that, as the waves are coming by, there's you might not be sampling the flow as it's coming by. If there's a vortex in between the waves as they're coming by, you might not be sampling the center of the vortex as it's coming by, and the vortex might be tilted as it's coming by. So you're not getting this sort of clean sinusoidal pattern in the flow. It's actually much more complex as it's going by the fixed point mooring. The other thing that I want to show is that, as I said in the previous plot, where you see the largest temperature signal is around the thermocline. So you have the largest subsurface temperature signals between 60 meters and 120 meters. And when you have this southward subsurface flow at the beginning of the wave, that's when you have a warming anomaly and a deepening of the thermocline. And when you have, then later on, when you have a cool anomaly, you have the shoaling of the thermocline. Okay, so I mentioned vertical propagation here for the TIW composites. So if I look at the whole record, I'd see vertical propagation, but I wanted to really hone in on what the vertical propagation was looking like. Was it really what was happening during the TIWs or other times through the year? And it turns out that that when you really see this vertical propagation is during the first 3 TIWs and during the second 3 TIWs. And what I'm showing in this figure is a lagged correlation between the velocity at 67 meters. So this is between the meridional velocity at 67 meters and all of the velocities above it. And what you can see is that the correlation is highest at progressive lags. So when you're close to the mooring, there's not much lag. And as you move to the surface, the lags are about 3 to 4 days when you see the maximum correlation. So that's consistent with sort of this is consistent with the upward phase propagation. And what we found for the first 3 TIWs were speeds of about 14.4 meters per day. So it takes between 3 and 5 days to reach the surface, those signals. Okay, so we have this really, tremendous structure. We have vertical propagation. We have perturbations that reach down to 87 meters. Models usually have 5-day averages. They usually have, or 3-day snapshots or monthly averages. So do we still see this if we do a 5-day average? Do we see kind of this rich structure if we apply a 5-day average? The answer is you still see the tropical instability waves. You still see their influence, reaching down to 67, 87 meters. You still keep some of that structure. You lose some of that shear that we had observed. That rich structure in the shear kind of washes away. But they're still there, and you still have identifiable TIWs at the surface and in the subsurface. If we compare with GODAS during the same time period, so this is a simulative model available as 5-day averages, during the same exact time period, it doesn't have much tropical instability waves at all. It has much stronger eastward flow. The shears are much weaker. And you maybe see TIWs later in the year, and you don't see much of a signal at all at the surface of the flow. So this is one model of many. Maybe other models get the structure right. Maybe when this model is assimilating temperature data, and maybe that process, which it's been observed, it's been noted that this happens in assimilative models, that they tend to damp out tropical instability waves. The model generates its own instability wave, and when you assimilate observations, you're shifting the structure at the expense of the amplitude of the waves. So maybe that's what's happening. But the value of this data set is that you can do these comparisons, and I think you can try to point to maybe things that the models and the assimilative models might not be getting quite right. Okay, so this is my summary slide, but it's a fake summary slide because if I have time, I'll show you 5 more slides. But we'll see. What I want to tell you about the first year of TACO's data is that we have, this novel continuous in time data set that captures horizontal currents and shears in the tropical North Atlantic. And those shears impact temperature and they impact the thermocline. Things that were surprises to me, maybe not to you, was that the mean velocity was strongest between 32 and 37 meters, as were the shears. The near surface currents were a lot weaker than I expected based on long-term measurements. We had really, quite strong and energetic tropical instability waves, despite the fact that the cold tongue was warm, and past knowledge tells us that should be a weak year for the tropical instability waves. Based on our experience at the equator, we might have expected to see zonal velocities really dominating the story. But during the first year of TACO's data, we had the largest fluctuations in meridional velocity, and they reached all the way down to 67 or 87 meters depth. Despite that, I was also expecting the shears to be largest during the tropical instability waves. But it turns out that the shears were largest before the TIWs even started and after the last TIWs ended. And that was the time period when the mixed layer depth, the thermocline depth, all of that was shallowest. So maybe it's just seasonal variability that's really dominating the shears at 4 North. I saw that if you subsample TACOS 1 to the TACOS 2 configuration, you missed a lot of those high shear events. So high vertical resolution is really needed to capture those strong shear events. And I showed you one example, but there's other examples. Models tend to underrepresent TIW amplitudes and the associated velocity and shear perturbations that we see during the TIWs. Okay, so if I have 5 more minutes of your time, I'll show you some ongoing analysis of TACOS 1 and TACOS 2 data, because the data is coming in real time. So even though it's only been in the water for about 6 months, we can get the data every day and look at it. But before I show you TACOS 2, I will just show you some work that Greg Foltz is leading. And the take-home messages from this, he's using a KPP model and using the TACOS data to estimate vertical turbulent cooling. And I know I'm short on time, so the blue line is showing you when you have the highest mixing at the base of the mix layer, and the red line up here is showing you when you have the largest turbulent cooling signal. And those are all when the mix layer is shallow and when you have really large shear in the data, when you have those 2 things happening. So having shear is important for mixing and turbulent cooling at 4 North. You can also look at the seasonal heat budget in below the mix layer, and use the KPP model and the TACOS data to tell you what the vertical turbulent cooling is. And you can also filter the data, remove out the diurnal variability, remove out the TIWs, and see what their impact is on the heat budget. And so the black line is the vertical turbulent cooling using the full data with no filtering. The the magenta line is what happens when you filter out periods associated with tropical instability waves. So it matters, but not that much to the seasonal evolution of vertical turbulent cooling at 4 north, 23 west. It really matters at the equator, but at 4 north, 23 west, maybe not so much. But when you take out those, so now what happens if you take out those super inertial oscillations that we noticed were in the data set? So there's sort of these super inertial variations happening all throughout the data set. I just called out, one period of time when you have variability on that 4 to 7 day window. And that removing that is the blue line. So that also, affects the vertical turbulent cooling. But the thing that had the biggest effect, other than simply giving it constant shears the whole time throughout, was when Greg removed the diurnal variability. So when he applied is a 1 day low pass filter to the data?
Removing all periods less than 1 day.
Right. So when he moved all periods less than 1 day, that really is what changed the vertical turbulent cooling. And so that really high frequency variability that we sampled during tacos is what's really driving the vertical turbulent cooling at 4 north, 23 west. Okay, and this is at the level below the mixed layer. So this is pretty deep in the water column. This is not up at the surface. This is, on average, the mixed layer is in the range of like 50 meters depth. So it's not happening at the upper instruments. Okay. Jonathan is leading a study looking at the diurnal cycle analysis. And so he's making these diurnal composites every season in the data set. And what he found was he found the strongest diurnal variations in meridional velocity in June, July, and August when you have these tropical instability waves. And that's what these vectors are showing. This is the diurnal. So this is as a function of hour and depth, a composite in June, July, August. The colors are temperature. And then the upper panel is the anomalies of the winds as a function of the diurnal cycle. So he finds that there is a significant diurnal cycle in meridional velocity in June, July, August when these TIWs are present. And so you have a northward acceleration of the flow as the surface warms, and this black line is the depth of the mixed layer. And so you can see the depth of the mixed layer also shoals during that time. We're still trying to understand what the winds are doing, why the winds would have a diurnal cycle. There's not, it turns out, many observations that have hourly data that we can compare against, nor are there models that have, easily available that kind of resolution to look at. So we're still trying to understand what's happening with the diurnal variations in the winds. But the mean wind flow is northward. So this is just strengthening and weakening the prevailing winds. It's not changing the sign of the prevailing winds. The other thing that's interesting is subsurface. Below the mixed layer, there's a semi-diurnal variability that's coming up. And Greg has started to look at some preliminary analysis, and he thinks it's not the diurnal cycle, it's semi-diurnal tides that are going by the mooring. And so that is what, in his study, had the biggest impact on the seasonal vertical turbulent cooling, those semi-diurnal variations. So stay tuned for more on that. Okay. Just to show you the Tacos 2 data that's come in. So I've just stitched together, again, this is the full Tacos 1 ending here. And I've stitched together the data that's coming in from Tacos 2. And so what you can see is that the flow is, we've got these really strong intra-annual, intra-seasonal variations that, in this year we had a much stronger zonal anomaly than we had all throughout the previous year. And you really see that when I apply a 30-day low pass. So I do a monthly mean, and you really see that signal pop out that the flow at the beginning of Tacos was really strongly eastward, and there was a much stronger southward flow. Okay, so there is year-to-year variability, but there's really strong monthly variability that can come in. And so if you average from March to March, you might see something totally different than if you average from the calendar year, or if you average over the long-term record. So anyway, it's fascinating. Data still coming in. Stay tuned. I just to kind of finish the loop on this, I took the early estimates from the first year of data, and when I had the same depth in both records, I plotted what the updated means would be. So this is the blue dots are the means from a year and a half of data. So that's just looking to see if the flow changed when the record length changed. And so, kind of stay tuned to see what happens as we collect more data. They overlap within the uncertainty of the estimates. So, but there's a tendency for the flow at all depths to become slightly more eastward and slightly more southward as more data is coming in. But again, there's all these really strong intra-seasonal variabilities that you can't, you have to really, have a long record to get rid of them and look at the long-term mean. Okay, so the future plans. So other than continuing to collect this data, which is so, fascinating and interesting to puzzle along and try to understand what the differences are between the two deployments. Our future plans is to redeploy the full array of instruments in February, March 2019. So we're going to do TACOS 3. And so, based on what we've learned, you want to have as many sensors out there as possible because you have these really short vertical scale shear events, and we don't want to miss them. To avoid future interruptions to the TACOS record, it would be great to have, a complete set of spares so we could do a swap at sea. So that we don't have to, rely on the kindness of our colleagues to loan us instruments and to be able to do, to have continuous turnarounds. The other thing that would be great, we captured all of this fine scale shear. We might be missing shear on even finer scales. So one thing that has been deployed at the equatorial mooring and we could consider doing here is to deploy in the buoy bridle looking downward a 400 kilohertz profiler so that we could really get fine scale vertical shear structure in the surface mix layer and, learn new things about the vertical shear. That is it. Thank you for your attention. TACOS would not be possible without all of these people who contributed resources, support, deployed the instruments, recovered the instruments, helped me analyze the data. I also, want to thank David Legler, Jim Todd, Sydney Thurston at the OOMD, soon to be GOMO, and to the Parada SSG for allowing me to do this process study in the middle of the Parada array. So, yeah. So thank you for your attention, and I'll take questions.